block is displaced 5 meters and the coefficient of kinetic friction is 0.300. Find the work done on the block by A, 70 Newton force, B, the normal force, and C, the gravitational force. D, what is the increase in internal energy of the block surface system due to friction? E, find the total change in the block's kinetic energy.
I'm sorry, what was the E?
Find the total change in the block's kinetic energy.
Oh, the change in kinetic energy. That makes sense. Okay, that's not enough. We're going to assume that the initial velocity is equal to 0, and we're going to find the final velocity as well, because there's not enough there. Okay, so we have a block. We're applying a force to it. We know it has a displacement to the right, so we'll actually put delta R is equal to 5I meters. And we're looking for the work done by all the forces, each individual force. Step 1. Let's give me a step here. The first one. Justin.
Draw a free body diagram.
Free body diagram. Give me all the forces in our free body diagram, please. Show me. Force of gravity down. Force applied goes in that direction, thank you. So the force applied is at an angle of 20 degrees above the horizontal. And the force of kinetic friction, which is going to be to the left. Good. We've drawn our free body diagram. Class, what now? The force applied, you can see, will break into its components. So the force applied is equal to, give it to me in terms of I and J, please. Quick.
So force applied equals force applied in the x direction times I.
What's force applied in the x direction?
Force applied times cosine theta times I plus force applied sine theta times J.
Great. Force applied is 70 cosine of 20I plus the force applied 70 times the sine of 20J. Could I please have these numbers? Great. So we now have the force applied in newtons. So let's sum the forces. The net force is going to be equal to, you can see we have all the forces. We're going to do it differently this time. We're going to do it in all directions all at the same time, just for fun. We have the force applied, we have the force of gravity, we have the force normal, and we have the force of kinetic friction. That's all equal to mass times the acceleration. Right, we have all those forces. In terms of I's and J's, we have I, 65.778 I, plus 23.941 J. That is the force applied. What is the force of gravity in terms of I's and J's? Sure.
It would be 0I.
True, I'm not going to write the 0I, but yes, 0I. Negative mg times j, because it's in the negative y direction, and the equation is mass times the acceleration due to gravity. Okay, well, we can do the same thing with the force normal. The force normal is just force normal times j, because it's in the y direction. And then we have the force of kinetic friction. We have the equation for that. It's uk times the force normal, and we even have a direction. So it's plus a negative uk times the force normal in the I direction, because it's to the left, or the negative I direction. That's equal to mass times the acceleration. Okay, well, we know something about the acceleration. We can write an equation for it. What do we know about the acceleration? These.
It is.
You don't need one. No. You need to think about what's going on in the problem.
Is it like
what do we know about the acceleration, Nick?
0.
The acceleration is not 0 completely, but we know acceleration will be
Is 0 in the y direction?
in the y direction is equal to 0. So what I'm going to write is the acceleration in the x direction times I, and just to be clear, I'm going to put 0j, just to identify specifically that's where that comes from, because the acceleration in the j direction is equal to 0. So you can see, rather than writing two different equations for net force in the x and the y direction, we can do it with one. We can then, of course, split up what we know into the I and j directions. So let's just look at the j direction. If we look at the j direction, you can see we have 23.941 minus mg plus the force normal is equal to 0, right? Just pulling out all the j's here. So then we get that the force normal is equal to, bringing the force normal over to the other side, or actually bringing all these things over to the other side, we get mass times the acceleration due to gravity minus 23.941. We have, I believe the mass is 15, the acceleration due to gravity 9.8, minus 23.941. We have just figured out the force normal. Hold on a second.
0.0586.
We'll go 1.059. Great. We have the force normal. We can now just look at the i's. If we look at the i's, we have 65.778 minus uk times the force normal. Well, the force normal is mass times the acceleration due to gravity, and that's equal to mass times the acceleration in the x direction. So we can figure out the acceleration in the x direction. It is equal to 65.778 minus mu k times mass times the acceleration due to gravity divided by the mass. The acceleration in the x direction. Oh, actually, no, who did that? I did that. That's sad, isn't it? I apologize. That's times force normal, and we have a number for the force normal. You did that. 778 minus mu k, which is 0.3, times the force normal, which we just figured out, 123.059, divided by the mass, which was the acceleration in the x direction.
3.95166.
What do we get? 1.92. Independent confirmation, 1.92. Any more sig figs on that?
402.
I'm sorry.
1.92, 402.
402, so we'll just go 40. Okay, meters per second squared. Now, if you look, we can use uniformly accelerated motion. We can say that what are we looking for? The final velocity, we have the acceleration, and we have the change of position. So we could say the final velocity in the x direction squared equals the initial velocity in the x direction squared plus 2 times the acceleration in the x direction times the displacement in the x direction. So velocity initial was 0 plus 2 times 1.924 times 5. We get that the square root of that is equal to the final velocity in the x direction. The final velocity in the x direction equals
4.3864.
with sig figs 4.39 meters per second. Great. We just figured out the final velocity. We know it's completely in the x direction. 4.3846 or 64, yes? Okay. Great. As of yet, we haven't answered any of the questions they have asked. But we're close. Work done by the force normal. We are, of course, going to use the dot product of force and displacement because these are all constant forces. Everybody see that? There are no integrals here because they're all constant forces. So we simply have the dot product of the force normal and the displacement. So 123.059 J dot product with the displacement, which was 5. That's 5. Yeah. Okay. 5 I. Work done by force normal. You should know it even before we put anything down. 0. Because the angle between the force normal and the displacement is 90 degrees. Cosine of 90 is 0. Good. Work done by the force applied. It's going to be the dot product of the force applied and the displacement. 65.778 I plus 23.941 J, dot product with 5I. Again, we multiply the I's and J's together, 65.778 times 5 plus, just for clarity's sake, 23.941 times 0.
328.89.
328.89 with sig figs, 329 joules. Good. Work done by the force applied. Work done by the force of gravity. It's going to be the force of gravity dot product delta R, or mass times the acceleration of gravity times J, negative dot product 5I. I don't have to plug any numbers. We already know the work done by the force of gravity is? For the same reason the work done by the force normal was 0. The work done by the force of friction, dot product of force of friction and the displacement. Negative UK times the force normal times I, dot product with 5I. It's going to give us negative 0.3 times our force normal, which was 123.059, times 5. Work. Great. Negative 185 joules. We have answered parts A through C, the work done by all of the various forces. Part D. What is the change in internal energy of the block? Okay, so think of it this way. We have an object sliding along. It slides along. The energy, as it slides, it loses its kinetic energy, right? Where does that kinetic energy go? Friction. Where does the friction take it? Heat, light, sound. In this class, we're going to assume that it all goes into internal energy as heat. The change in internal energy, which is a good assumption, is pretty close. The change in internal energy is equal to the negative of the work due to the force of friction. It equals negative of negative 184.588, or 185 joules. Okay, next. The change in kinetic energy. Gosh, I don't know. Change in kinetic energy. How do we figure out the change in kinetic energy from what we have here? Carolyn. I know. You can do it that way. That's not how we're going to do it. Kevin. The net work equals the change in kinetic energy. Change in kinetic energy then is going to be 0 plus 328.89 plus 0 minus 184.588. The change in kinetic energy. 144.305 with sig figs 144 joules. Okay. Good. Now, it asks, we could go through and figure out the final velocity. We're not going to do that. You can see that this is equal to change in kinetic energy, so it would be equal to 1/2 mass times velocity final squared minus 1/2 of mass times velocity initial squared. You can see that's going to work out to be exactly that. What we need to do instead is see this. The force applied transfers 329 joules of energy into the system. 185 joules of that energy goes into internal energy of the system. The remaining energy, 144 joules, goes into changing the velocity or changing the kinetic energy. So notice, the force applied, it puts 329 joules into the system. Some of that energy goes into changing the motion, right? Changing the kinetic energy. But some of that energy goes into internal energy as heat. It heats up the object. In other words, the change in energy of the system is equal to the net energy transferred. That's a capital T for transferred into or out of the system. In other words, this right here is the change in the mechanical energy of the system plus the change in internal energy of the system equals the energy transferred into or out of the system. In other words, the change in mechanical energy, the only change in mechanical energy in this particular case was kinetic energy, 144 joules. The change in internal energy was 185 joules, and we put 329 joules into the system. That's how much we put in. Less than half goes into kinetic energy, motion of the object. More than half, in this particular case, went into a change in internal energy. It heated up the system.